Hi, my name is Bardia Tagavi, and today I want to present my lecture about processing encrypted data. Let me first share my screen. Okay. I have done a comprehensive survey on processing encrypted data about advancement challenges and future directions in processing these data. First, about the highlights of my presentation. First, I will talk about the overview of encrypted data processing technique, different techniques of processing these types of data. And after that, I will briefly talk about applications in different fields such as cloud computing, healthcare, financial fields, government, and so on. After that, I will provide a brief background about the basic of the cryptographic, such as symmetric and asymmetric encryption algorithms. And the main body of my presentation is about the techniques of processing encrypted data. I will elaborate this section and I will discuss in detail. And finally, I will talk about the challenges and the future research directions in this field. Okay, we live in a world with a tremendous amount of digital data, and many of them contains sensitive information. So we cannot store it or transfer it in a plain text. We have to protect this data, protect this sensitive information. And there are several schemes, several methods to protect data. They're called encryption. We encrypt the data, store it or transfer it to another location. And after that, when we want an information from the data, we can decrypt the data and retrieve our desired information from the data. However, it would be the violation of purpose if we decrypt the data. If the data is decrypted, it would be at risk. An adversary can easily read the data, can easily attack the system, and find the unencrypted version of the data. So there should be a way to do the computation and do the calculation on the encrypted version of the message and data. And about the importance of this processing, and they find their ways in many fields such as cloud computing, healthcare, database systems, financial services, machine learning on a data set which is encrypted, and the most important one is the government and military. First one in the cloud computing, for example, HELIP by IBM is a library for do some computation on a data that is stored in a cloud. Or in healthcare, there are many information of patients, their medical records that they are very sensitive information, and we have to protect it, but we want to retrieve some information from the data. And another one is the database systems. For example, the CryptDB for SQL queries are one of the examples that we can do a query. We can send a query to a database without decrypting the database. We can encrypt the database, and by sending a query with this library, we can retrieve the key and the value from the database. Or the financial services, which are among the most targeted fields in the world by the attackers, because the money is one of the best motivations for the attackers. Or for machine learning on encrypted data. In machine learning, many times we have a data set that is encrypted or gathered from several sources of information that we have to preserve the privacy of the data set. So we have to encrypt it and do the machine learning inference and learning, training and testing and inference stages on the encrypted version of the dataset. For example, one of the best library for this is Seals from Microsoft that enable us to do the machine learning on encrypted dataset. And the most important one is the government and defense, because it's related to life of the people. It's related to the highest confidential data that's provided by the government and gathered from every person in a nation. And it's very important, especially in a war or in a cyber war. And they should be protected at any cost. And my motivations for this study was about the increasing need for the protecting the data, because the digital world is growing rapidly and we have to protect it in a better way. And we have to set some regulations, some standard regulations for this protection. And because these methods are relatively new, there are some new challenges and some new problems that should be addressed. And the quantum computers are emerging. They can be they are potential threats now. They are so much faster than traditional computers, and we have to prepare an algorithm that cannot be broken easily by these quantum computers. And my contribution to this study is I investigate the application of these methods from many perspectives, from different perspectives. And I critically analyzed an advancement in different papers. And after that, I highlight the future research directions. Finally, I will discuss about some standardization needs for an agreement between different parts of a network. Okay, for the background part of encryption. As you know, we have some messages that are in an encrypted manner, and everybody can access everybody who can access to this data can retrieve their desired information. So we need a key to encrypt this data, and for another key or the same key for decrypting it. If both keys are the same, we have symmetric encryption, and if they are different, we have asymmetric encryption. And the ciphertext would be our goal to do the computation in my survey. Okay, for the symmetric encryption, as I said, only single key would be implemented for encryption, both encryption and decryption. They are relatively faster, but they are less secure. For example, AES, DES, or triple DES, RS2, RS6 are some examples of symmetric encryption. And for the asymmetric encryption, public key and private key are a pair of the keys for encryption and decryption. They are more secure, but they demand higher computational overhead and maybe more complex. But we have a third encryption method called homomorphic encryption. In a homomorphic encryption, we can do the mathematical computation and calculation on a ciphertext without decrypting the data. The data can be encrypted, stored, or transferred, and when we want to do a computation on the data, we don't need to decrypt the data. We can just implement the function, the calculation on an encrypted version of the message. So they will be more secure, but obviously they will be more complex than the traditional ways. And there are three types of encryption called partial homomorphic encryption, somewhat homomorphic encryption, and fully homomorphic. Fully homomorphic encryption was introduced by Rivest, Altman, and Dieterzus in 1978 in an RSA scheme. We know it by RSA scheme today. But after year 2005, Dr. Bone take a huge step in homomorphic encryption and in somewhat homomorphic encryption, especially. And after that, his PhD student on his thesis, Craig Gentry, introduced the first feasible fully homomorphic encryption. Homomorphic encryption is such as this is an analogy to better understanding of homomorphic encryption. For example, think you have a store of a jewelry and you want to make some jewelry with some workers. But you cannot trust the workers. So you put some gloves on an impenetrable box and put the gold on the box. And when a worker wants to build the jewelry, they can put their hands on the gloves and build the necklace or a ring. And after doing their work, they will put take their hands out of the gloves. So they cannot take the gold out. And this gold is the data that we have, and the necklace is the computation that we perform on a data on a homomorphic encryption, and the homomorphic encryption is the gloves in this analogy. And this block diagram states that when we have a message, and after encrypting it, we have an encrypted off message. But when we perform an F, when we pass an encrypted message to a function, we will have F of encrypted of M. But there's no difference between F of encrypted of M and encrypted of F of M. There's no difference. In a homomorphic encryption method, there's no difference between these two expressions. Partially homomorphic encryption, or PHE, supports only a single type of operation, such as addition or multiplication on a ciphertext. For example, RSA, which is introduced by Rivest, is an example of PHE, which supports multiplication, only multiplication. We cannot perform addition on an RSA scheme, on a data which is encrypted by RSA scheme. And they are much faster than other types, but the functionality is limited, as you can see. We have only addition or multiplication. For example, this is a table that summarizes several notable works in PHE schemes, and it shows that Rivest and El-Gamal enable us to do the multiplication on a ciphertext without decrypting it, and the other works allow us to do the addition, only addition or multiplication. But somewhat homomorphic encryption, or SHE or SWHE, supports limited addition and multiplication, but the combination of these ones. We can do both addition and multiplication, but limited time. We cannot do unlimited times as we want. They are more capable than PHE, but the complexity is more than PHE. But there's a balance between the security and the computational overhead in SHE. And today, despite the fact that fully homomorphic encryption are improved a lot, we still use SHE encryption in many cases because the computational overhead is very well studied and very improved. They are very improved scheme, very efficient scheme, and they provide a good security. Although the security is less than fully homomorphic, but it can be acceptable in many cases. And you can see in this table some notable works on SHE schemes. For example, the best one, in my opinion, is Bone, called BGN scheme. Because before Dr. Bone's research, the ciphertext, as you can see, will grow exponentially or linearly, but in BGN there is a constant size of ciphertext. And after Dr. Bone, his student, Mr. Gentry, introduced introduced in his dissertation the first feasible fully homomorphic encryption, which enables us to perform unlimited additions and multiplications on a encrypted message. We can do any computation on the data, and it is obvious that it would be a very complex mathematical computation, and it would demand a very high computational overhead. But it's very powerful and very secure. And there are 4 approaches based on 4 different types of hardness. This hardness will describe how the encryption scheme would be broken. And they are based on 4 different types of problems in the mathematical world. Gantry approach was based on lattice, which is introduced many years ago, but Rivest introduced it into the encryption world, and Gantry used the lattices on this approach to reach the fully homomorphic encryption. But there are other types of hardness, such as AGCD or LWE and ring LWE, which is a variant of LWE, and NTRU based, which is somehow related to ideal lattice-based schemes. And this is a table that summarizes the differences between FHE and some SHE, somewhat homomorphic encryption, and partially homomorphic encryption, that I described in details in previous slides. But homomorphic encryptions are not the only way to do the computation on a ciphertext. There are other ways, such as order-preserving encryption, which allows to do some sorting or ranking on a data which we want to preserve the order of the messages. It is obvious that it's not a very secure system, although it's a little secure, but it's not so secure system. But for sorting, these algorithms and these schemes are very fast. Or searchable encryption. We can search a query or anything that we want on a data, and this encryption method especially designed to perform a search on a encrypted data. And one of the most trending research these days are secure multi-party computation or SMC. Secure multi-party computation enables some nodes in a network to collaborate with each other in a very secure manner. Every node in a network may contain sensitive information that they don't want to share to another nodes, but they want to gather the information and perform a calculation on a on an entire information that gathered. A secure multi-party computation is the best way to do this. But there are some challenges in homomorphic encryption. One of them, as I stated earlier, is high computational overhead. They are very, very complex algorithms based on very complex mathematical problems. So the implementation would not be easy. And we cannot use it anywhere we want. We cannot use it in any system we want, any hardware. And there are some limitation in implementation and the hardware and software that is needed. And because this is a relatively new encryption schemes, although it's dated back to about 40 years ago, but because the improvement in this field is relatively there is no standard way to do the homomorphic encryption. And so there would be a way to, several nodes and several party can come to an agreement and to do the encryption. And adversary operations is always an issue. An attacker can do their desired operation on a ciphertext because the scheme allow anyone to do the operation. And also they can implement their malicious software on a ciphertext, and it may be harder to detect. And for the future research directions, as I mentioned many times in my lecture and my presentation, the efficiency of homomorphic encryption is the biggest issue. So if we want to use the fully homomorphic encryption schemes which are very, very secure, we have to improve the efficiency of this encryption. And we have to be prepared for the quantum world, for the quantum systems. And we have to prepare and develop some encryption methods that cannot be broken easily by quantum computers. And machine learning is one of the most trending science today in many applications. When they have to learn on some data. Many of these data can be private and contain sensitive information. Privacy preserving machine learning techniques is so crucial today. And the scalability is a problem in encrypted data processing that should be addressed. And as I stated in the previous lecture, standardization should be done. And we have to develop a consistent protocol among different companies. And different companies have come to an agreement to these protocols. For the conclusion, first, I want to summarize about my talk. I talked about encryption schemes and its applications, and different schemes of processing encrypted data, such as fully homomorphic, partially homomorphic, somewhat homomorphic, order preserving, searchable encryption, and SMC, multi-party computation. And after that, I talked about the key advancements and the needs and the limitation challenges and what we have to do in the future and to prepare a very, very reliable protocols, reliable schemes, and reliable encryption algorithms to be prepared for quantum world, be prepared for the rising of AI, And this method would be the best method because their security is at the highest level. And thank you for your attention. Thank you for your attention. ای بابا.
آفرین عزیزم. چند بارشه؟ چی؟